Okay, so far we have seen a linear model with numerical predictors. We have seen how to model categorical predictors and how that involves adding new terms into the model, the dummy variables. Now, in a sense, those are measuring or those are modeling the main effects of those predictors. So what is the effect of x1, what is the effect of x2, and so on and so forth. But as we saw in the block on methods, we are probably interested as well in the interaction between those predictors, between x1 and x2, for example. So it's not only about what is the effect of x1 on y, but what is the combined effect of x1 and x2, or of a specific combination of x1 and x2. And very often, this is what we want to look into. So far, the assumption was, what is the effect of a unit increase in x1 regardless of x2? Well, that regardless is not really realistic. In reality, those two have a joint effect on the response, and we want to be able to model that. So if we have two numerical predictors, say x1 and x2, how do we model the interaction between them? Well, we model them by adding a new term into the model that equals the product of x1 and x2. So the model now becomes something like this here. We go from the model of only x1 and x2 to a model in which we have the same plus this new term over here, which is the coefficient, beta 3, times a new variable that is the product of x1 and x2. So it's like we are including a new third variable equals x1, x2. Now, of course, the model has no idea where this x3 comes from. It's just like we previously computed this new predictor x3 equal x1 times x2, and we just give it to the model. That's exactly what we're doing here. And so if we do a little bit of manipulation here, what we see is that now the effect of x1 is not going to be only beta 1 as we had in here. The effect of x1 is beta 1 plus a certain coefficient times x2. And this coefficient, beta 3, is exactly the interaction. So what we're saying is the overall effect of x1 is beta 1 plus something that has to do with the value of x2. And vice versa. It's also the main effect of x1 is over here, all the same. But now the effect of x2 is beta 2, what we had earlier, plus a certain effect given x1. So a certain interaction between x1 and x2. The overall total effect of x2 depends on the value of x1. This is precisely the interaction. Let's take a look at the example. So we go back to the case of the sales of a product by advertising on TV and radio, for example. Let's compare the two models. In the model on the left here, we have only the main effects. So we have the main effect of TV, beta 1, and the main effect of radio, beta 2. We do OLS, we fit the model, and this is what we have. Let's say that we want to incorporate the interaction between TV and radio. How do we do it? As we saw, we have this new term into the model, TV times radio, and the corresponding coefficient, beta 3. This beta 3 is modeling the interaction between TV and radio. And if we do OLS, this is the model we have. So how do we interpret this? Well, first of all, let's see, the R square is going from essentially 0.9 in this model to 0.97 in this model. So apparently is giving us a better description of reality. It's able to account for an extra 7% or so of the variability. And the RMSE goes down from 1.7 to 0.93. So it's also improving quite a lot. The model, if we look into the magnitude of the errors, is actually giving better predictions. Why is this? Well, let's see specific cases. So in this case, the TV advertising has a positive effect on the sales, and it's kind of reinforced by the amount of advertising on the radio. So it's like the effect of the TV on the sales is not only this 0.019 we have here in beta 1, but also reinforced by this amount times what we advertise on the radio. That is the total effect of the TV in this case. So it's something that depends on the value of TV and also on the value of radio. That right there is the interaction effect. And of course, vice versa. What we're saying here is that the total effect of the radio is 0.029 plus the interaction times the TV. So it's like they're kind of reinforcing each other. Let's imagine that we see the advertising on the TV and we are more likely to buy the product. Sure. We hear about it in the radio. We are a little bit more likely to buy the product. Sure. What this is saying is that those two things are not independent of each other. That if we see the ad in the TV and we also listen to it on the radio, we are even more likely to buy the product. So they're kind of reinforcing each other. And by the way, we have something called the hierarchy principle, meaning that even if the main effects appear to be zero, like there's no main effect of TV, let's say this is very close to zero, or we could just assume it's zero. Even if that's the case, if we have an interaction involving TV in the model, we should always include the main effect as well. So what it's saying is, if we have a model in which we have, I don't know, let's say beta 0 plus beta 1 radio plus beta 2 TV times radio. What this is saying is, if we have an interaction having TV, like this one over here, we should always have the main effect of TV. So we should always have this term over here to always have all the factors involved in the interaction as we go up all the way up. So we have an interaction between three factors. We should have all the two-factor interactions, and we should also therefore have all the main effects. Because otherwise, they are confounded with the main effect, and the whole thing is very tricky to interpret. So every time we have an interaction, it's advised that we also have all the lower order interactions or all the main effects. It's just going to be easier to interpret. So, okay, this is how we model an interaction between a numerical and a numerical variable. What about an interaction between two categorical variables or two nominal variables? Okay, so what we can do is add one dummy variable for each combination of the two predictors. So let's say, again, for simplicity, we have two binary predictors, x1 and x2. They are equal to yes or no. Then it would be about adding three dummy variables. The first one, z1, would be the case in which x1 equals no. Zero otherwise, or yes, right? The second one, z2, is the one that does something similar with the second predictor. So if the second predictor equals no, then z2 equals 1. And if it's yes, then equals 0. And now we have a third predictor that is going to model the interaction. So it's going to be 1 if both x1 and x2 equal no, and 0 otherwise. And right there, we are modeling the interaction. So we are explicitly accounting for the case in which both of them are no. And by the way, beta 0 would be the case in which both of them are yes. So we'll have yes, yes. Let me show you specifically. So this would result in this model, the intercept beta 0 plus all the three dummy variables with their corresponding coefficients. And this would, again, be split into these four different models depending on the values of the predictors. So we have both x1 and x2 equal to yes, then we would have z1 equals 0. We also would have z2 equals 0, and we would have z3 equals 0. So this is only beta 0. Beta 0 in this case would correspond to a specific case, yes, yes. This would be the reference, and all the others would be deviations from it. So if we have a deviation of beta 1, that would be the case of x1 equal no and x2 equal yes. x2 is not active, so to speak, because it's equal yes. If x2 is active, then we would have x2 equal no. This coefficient is active, all the others are not. So the model translates into beta 0 plus beta 2. And if we have everything equal no, then we would have both beta 0 plus beta 1 plus beta 2 plus beta 3. This would be modeling, again, the interaction. The specific case in which x1 equal no, x2 equal no. And by the way, this z3 is actually computed as the product of z1 times z2. We are actually computing the interaction term by computing the product of the two dummy variables z1 and z2. And again, we could fit the model without an intercept. That would be adding yet another dummy variable, but it's going to start being tricky to interpret if we add more and more predictors. So let's see an actual example on what this looks like and how to interpret it. So in this case, we're going to try and model again the salary of employees based on two predictors, whether they have health insurance or not, and their job class. And specifically here, the job class could be industrial or IT. What does the model look like? Well, we know we have the intercept, beta 0, that's always in there. And now we have one dummy variable for insurance equal no. That's beta 1. Then we have another dummy variable, class IT, for the case of job class equal IT. And then we have the third dummy variable that is modeling the interaction, insurance no, class IT. And so whenever these two dummy variables equal 1, then beta 3 would be active and we will have the interaction. So let's see. We get our data, we go through OLS, we fit the model. These are our estimates. What do they mean? If we take a look at the intercept, that means insurance equal yes and class equal industrial. So this 112 is giving us the estimate for the group of yes insurance industrial. So it would be actually this one over here, 112, that would be beta 0. Any other case different from this one would be a deviation from beta 0. So let's say we are still in an industrial class job and we don't have insurance, then that would be beta 1 because insurance no will be active. This would become 1 and still class IT is 0 and the interaction would still be 0. So we are in the case of beta 0 plus beta 1. What does that mean? It means we take the intercept, 112, and we subtract 24. And that would be this deviation over here. That is minus or plus beta 1 because it's negative. So what this is saying is for the industrial setting, if you don't have an insurance, you have a negative effect on the salary of 24 units. If you are still in the case of insurance, yes, and now it's not industrial setting but IT setting, then you have a positive effect of plus 15. So what this is saying is the distance from here to here is plus 15. Again, this will be the model in which only beta 2 is active, only the class IT dummy variable equal 1. And the final case, it would be insurance no, class IT. And in this case, beta 3 would be active, beta 2 would be active, and beta 1 would be active as well. All three deviations are active. So what this is saying is if you don't have an insurance and you go to class IT, then the final estimate would be intercept minus 24 plus 15 minus 4. So that would be the distance between beta 0 and the estimate over here. And so this is how the model is allowing us to incorporate two categorical predictors and their interactions. We have to keep in mind the very important fact that the intercept corresponds to one specific combination of the two factors. In this case, this is insurance equal yes and industrial setting. Anything that deviates from that specific combination is going to be modeled by the three coefficients, beta 1, beta 2, beta 3. And in the end, all these estimates are giving us the necessary numbers that we have to put together to add and subtract in order to compute the estimate for one specific combination of the factors. And finally, we have the interaction between a numerical predictor and a categorical predictor. And specifically, let's say that x1 is numerical and x2 is nominal or categorical. How do we do it? Well, what this is going to do is model one slope for the numerical variable per level of the categorical variable. So what it's going to do is tilt the line up or down depending on the specific level of x2. So again, for simplicity, let's say we have a binary categorical variable, only yes or no. What we do is include a new dummy variable. Let's call it again z. What does the model look like? We have, again, the common intercept. We have the slope for the first coefficient, which is numerical. We have the deviation from the intercept for the categorical variable. And then we have the interaction, beta 3. This beta 3 is modeling the deviation for the slope. So if we look at again at the model from the perspective of the two possible categories, yes or no, if the categorical predictor equals yes, then the model reduces to beta 0 plus beta 1 times x1. So we have the intercept beta 0 and the slope beta 1. This is how to interpret these coefficients. Beta 0 would correspond to the intercept for case x2. And beta 1 would correspond to the slope of x2 equal yes. And now if we have x2 equal no, then we have two changes. First of all, we have a deviation for the intercept. Now it's not going to be only beta 0, it's going to be beta 0 plus beta 2. So that right there is the main effect of the categorical predictor. It's a deviation for the intercept, up or down. And then we also have a deviation for the slope. So what multiplies x1 is not only beta 1, it's beta 1 plus beta 3. So it's the main effect of beta 1 plus beta 3. This would be the slope for the group x2 equal no. And so what this interaction is giving us is one specific slope and intercept for each of the two levels of the categorical predictor. So what does it look like? Let's say we go for the very simple case. Here we're trying to model the wage of an employee as a function of the age. This is our numerical predictor. And we go for the simple case, just a linear model of one numerical predictor. We fit the model. This is what we have. Intercept kind of 82, slope 0.71. So what this is saying is the effect of the age is 0.71. Yeah, like your salary increases 0.71 units by year. This is what it looks like. Fair enough. Let's start adding more predictors. So let's say we want to look into the effect of having insurance or not. And so for reference here in gray, I have the first linear model with only the age to compare. And now if we have the main effect of the categorical predictor, that means we have two lines. And the difference between the two lines is how up or down they are along the y-axis, because what we have, the only difference is a deviation from the intercept. This is what the categorical variable is doing. So we have two different intercepts and the same slope. And so how do we interpret the model? Well, in here, insurance equal no would be the value for the dummy variable equal 1. So by default, the intercept would be insurance equal yes. And so what this is saying is 96 would be the slope, the intercept over here. A negative deviation of 26 units would be the intercept for insurance equal no. And in both cases, the slope for the age is 0.56. So the slope for both lines is the same, is beta 1 equal 0.56. So in this model, what we're saying is the effect of the age is the same regardless of whether you have insurance or not. What changes is where you start from. Do you start at 96 or do you start at 70? Let's say we want to add the interaction effect. So now we have a new term, beta 3, which models a deviation for the slope. So now we're going to allow the model to have a different slope, a different effect of the age, depending on whether the person has insurance or not. And so we have two intercepts and two slopes. Again, for reference here, we have in gray what the simple model would be. And now what we see is, indeed, two lines that are not parallel anymore. So we are not forcing the model to say that the effect of the age is the same in the both groups. And we are also allowing for a different intercept. How do we interpret the model? The intercept now, beta 0, would be, again, the insurance yes. So is what is the intercept of the group insurance yes? It's about 100, so it's this point over there. Then beta 2 is still the deviation from the intercept for the group insurance equal no. So it's now a negative 38. So it's about there. This is the effect of beta 3. We go from there to there. And then we have beta 1. Beta 1 would be the effect in this case of the H for the insurance yes group. Because if we were insurance no, we would have a deviation beta 3. So what this is saying is that the slope of the blue line over here, this one is 0.45. And the slope for the red line would be 0.45 plus 0.3. The combined slope for the group no is beta 1 plus beta 3. And so the model here is allowing us to, again, have two different effects of the H. We are not saying both groups must have the same effect of the H. It could be different. That's what the deviation beta 3 is allowing us to do. And we're also saying that both groups might start at a different point along the y-axis. Now, in some situations, you might be interested in saying, okay, I want to have two different slopes because the effect of the H might be different, but I want to force into the model that they have the same intercept. Maybe that makes sense. And this is one of the cases in which we may be interested in applying domain knowledge to force the model to say, hey, they have the same intercept, or they don't have parallel lines, or they do have parallel lines. This is where we apply domain knowledge. What would it look like? In this case, it would be one common intercept and two different slopes. So what we have now is one common intercept beta 0 at 85. That's this point over here. And then we have a slope of 0.78 for group yes. So that is the slope of the blue line. And we see we have a negative deviation for it, for the red group. So we have only here minus 56. And so overall, the slope of the red line is 0.78 minus 0.56. So we are saying that the effect of the H on the salary is lower when we don't have insurance. Our salary is going to increase at a lower rate when we don't have insurance. This is a case again in which we have one common intercept because it might make sense from a domain knowledge point of view, and two different slopes. We are allowing for the H to vary the salary at different rates. And so you see that interpretations become a little bit more difficult given interactions, and we are only having a one binary categorical predictor and one numerical predictor. So think about how complex the model could become when we start adding more and more levels and more predictors and more interactions. The whole thing would be a lot more difficult to interpret. And we will see later on, how to look into the model in a specific way to answer specific research questions, such that we don't have to make all these calculations ourselves. We just have to look into very specific places of a linear model table. Anyway, for these kind of situations in which we have different slopes, same slopes, different slopes across different groups, so many intercepts, etc., there's something called hierarchical models or multi-level models or mixed effects models. So they're models that are specifically designed for cases in which we have groups of data, and then we are going to allow the model to vary a little bit across the groups in a certain way to allow, for example, different intercepts, different slopes, etc., in a very specific way. So they have other theoretical advantages that we're not going to get into here. They're well out of the scope of this course. It's just FYI, if you want to look into these kind of situations, take a look at hierarchical models. And in general, we have to be very, very, very careful when interpreting these interaction effects, especially if we have more than two factors, because everything depends on what the reference, what beta 0 is modeling, what it refers to. And in the moment we start having more than two predictors or three predictors with more than two levels, etc., the whole thing is very complicated. And Again, in the coming videos, we're going to see exactly how to look into the model when we want to answer specific questions, but we shouldn't probably be looking into specific coefficients. We should be looking into something else. We will see what that is. Anyway, it's easy to misinterpret what those intercepts represent, or to misinterpret what specific combination of factors represents. It's easy to miss which coefficient should be active or not, depending on a specific case. So we're going to see different ways of looking into the model to answer these high-level questions. And we have to be careful, very careful, with just looking at the coefficients, with just looking at whether the number is positive or negative, or how big the number is. Because remember, we had this assumption that the coefficient only tells us something, holding everything else equal, holding all the other variables equal. And in reality, we never have something like everything else being equal and we just observe a change in one variable. We have to be very careful with comparisons of the coefficients because it also depends on the scale of the variables. If we have the information or data about the same phenomenon measured in centimeters or meters, the coefficients are going to be completely different, orders of magnitude different, but still they're measuring the same thing. So it's not just about how big the coefficients are. It's about more than that. And it's specifically going to be difficult to reason about coefficients if we have an imbalanced data set, an imbalanced study design. If, for example, one of the groups has many more observations than one of the other groups, it's going to make a difference. In the end, what we are typically interested in is in looking for comparisons across different groups of one categorical variable. So is the dependent variable different across the different groups of a categorical variable? Is the response different across treatments, for example, across countries, across programs, across whatever it is? And the linear model is going to allow us to make those comparisons while controlling for the other factors. This is why we might be interested in building more complicated models and why we have seen how to incorporate the categorical predictors, because in the end, in the next following videos, what we are going to see is how we can answer questions properly about different groups of one categorical variable while controlling for the other factors, and how to account for all the variability in the data, how to account for the sampling process, etc. Again, this is going to be very tricky with unbalanced data, but we will see how to try and correct for that when we look into specific hypotheses. In any case, what this is telling us, or is already hinting at, is that we should pay a lot of attention to the study design such that we have, in the end, a balanced data set when we start building a linear model, because making all these inferences about the data is going to be a lot easier if we do have a balanced data set.